name is Davide Poggiali. I'm a postdoc at the PNC, which is the Perugia Neuroscience Center. I work with medical images, and this is an MRI of my brain at the age of 27. And I'm talking about the fake notes approach, which is a joint work with Stefano, Francesco, and Emma, and everybody's in here, so thank you to the two others. Okay, so this is what I've been talking about. What are the fake notes? I will present some theorems about them, some numerical examples, and future works. All these slides are available online, so you can check out this website and try to move around the slides, even on your mobile phone if you want. Okay, interpolation of fake notes or interpolation via mapped basis is a technique that applies in principle to any interpolation method. It has shown the ability of obtaining a better interpolation in many cases without the need of getting new samples. I'll be more clear in the future about this. This means that if the original notes are a sufficient sample, it can be possible in principle to provide a smaller error interpolation. Let's talk about what it is in terms of code. This is Python code, but you can easily translate it to MATLAB if you're used to it. Suppose that you have some generic interpolation function that takes as an input samples and evaluating points. For instance, well, polyfit and polyval, just to be clear and simple. Okay, instead of calling the function directly, which is what we do now, even in numerical calculus courses, you can define a mapping function S and interpolate over the fake notes S of X. So, instead of calling, again, the interpolation of X, Y, X, X, we call this interpolation. So we evaluate both the interpolation points and the evaluating points over the mapping, and we call the same function. So it's very easy in principle to do that. Of course, it is difficult to choose a proper, efficient mapping. Okay, let's talk about this in symbolic terms. Suppose that we have a function and some samples of that functions on a set of nodes and a set of basic function, and we define as usual the interpolating function as this one under this condition, so nothing too new. What do we do using fake points is this. So we consider a set of mapped basis function, so simply the one of before composed by S, and the interpolant is now that one, which is the same thing but with bi of x and the usual interpolating condition. This process can be seen dually as two different and equivalent ways. So we can say this as an ordinary interpolation over the set of mapped basis, or a strange interpolation over fake notes. So an interpolation of another function g on the fake notes, which I defined before in the code, and g must be of any given continuity and must satisfy this. So if p interpolates g on fake notes with the original basis, this means that R, which is p composed by x, interpolates f. The second way is more useful for computation, and you see it in the code. I'll show you. So let's give some relevant theorems just to have some background to stand on. So we will make now two hypotheses. The first one is the map is injective. Under this hypothesis, the fake notes do not overlap. So this is really a simple assumption to make. And also, the function to be interpolated g is now such that G composed by F is exactly equal on F, and not only on the nodes. So such function G exists, not necessarily unique, provided the first hypothesis holds. Okay, let's give the first lemma. Suppose you have a cardinal basis that is representative of the basis set B I described it before. So, on the fake nodes, a cardinal basis on the fake nodes is such that this basis is cardinal to on the original set of nodes X. This has many important consequences. For instance, we have an equivalence of the Lebesgue constant. So, the Lebesgue constant of the fake node interpolation over the mapped basis is exactly the same over the fake node point. So we can switch from one set of nodes, in theory, if we know how we can, to another set of nodes that maybe has a smaller Lebesgue constants. The mapped basis interpolation, we have the very same Lebesgue constants as the fake nodes. Another theorem of stability, suppose that you have perturbated function values. Okay, the fake nodes interpolant is stable. So the difference is small provided, well, the perturbation is small and also the Lebesgue constant is small enough. This is kind of my favorite because we can have inheritance of the error bound. So, the method based interpolation inherits the very same error bounds of the original interpolation over the basis B. So, because the fake nodes interpolation, this one has the very same norm under the original nodes of the norm in every possible norm. This is important on the fake nodes of the interpolation over G. So this theorem is a link of the error bound. Suppose we use polynomial interpolation. So if we use the mapped basis, we have an error bound that works also for fake nodes interpolation. Let's see some example. Oh, this is a classical. The room effect in one dimension. We teach that in every, I believe, numerical course basic course. If we have equic space points, the error will increase dramatically with the number of nodes. So we can switch to another set of nodes, and so another set of samples in which, for example, the Chebyshev points in which the error must go stable and decreases with n. This is kind of a failure to me. It's always been quite frustrating because we're going to throw away data, and everybody that works with data knows that they're costly. And sometimes it's not even possible to get new data. So this is a very good example because I'm going to throw away the data of equispace sample to get new data. This is costly. Okay. What if we use a mapping that sends the equispace point to the Chebyshev-Lobato points? What if we try to do this? Okay. Let's try. This is the mapping that we use. This is a Runge function is in minus 5, and this is the mapping. This is what happens. Okay. Using the equispace nodes, we know the tune, the error increases, and the interpolation explodes. Using the Chebyshev-Lobato nodes, we have stability, and using the very same data as in the left, we can achieve stability. This is so a question arises: is it better to have Chebyshev-Lobato nodes or fake Cheryshev-Lobato nodes? Well, this is the error in black of the equispace points. In blue we can see the Cheryshev-Lobato nodes and its error, and in red we have the fake Cheryshev-Lobato nodes. So as you can see, after a certain number of points, Cheryshev-Lobato, true Cheryshev-Lobato outperforms the fake nodes interpolation. But, well, so far so good. We achieved that interpolation without changing data. I talked about the inheritance of the Lebesgue constant. Let's see the Lebesgue constant for the sampling 1D. So this is the Lebesgue functions, and the Lebesgue constant is at its maximum over 13 nodes in -5. We see what we see in the textbook. Nothing to see, nothing new. This is the Lebesgue function of the Cheryshev-Lobato nodes, which is smaller, so the constant will be smaller, and the constant is exactly the same of the fake Cheryshev-Lobato nodes obtained by using equispace samples. Let's move to the 2D. In a similar way, we can map a subsampling of the equispace grid into the so-called Padua points with comparable results with the 1D interpolation. So these in blue little are the nodes that we used. This is a subsample of the equispace N by N grid. If we map them into the Padua points, we can have similar results to actual interpolation on actual Padua nodes. Let's move to another application, another example called the Gibbs phenomenon. If we have a discontinuity in our data, we can observe some oscillation around the discontinuity points. So let us suppose that we know exactly where the discontinuities are, so we can divide into some subintervals the interval. So we map like this. We simply shift the nodes around the discontinuity points. So we add more and more and more. Here dk is the magnitude of the jump. So the value before and after the discontinuity. So the bigger, the higher the jump, the bigger the shift. Let's see some results. Okay, this is with equispace nodes. This is absolutely to be trashed in theory, because with equispace nodes, what do you have is both Gibbs and room phenomenon. This is what you get if you interpolate polynomially on the Cheryshev-Lobato nodes. So you can see the waves among the discontinuities. This is on the fake Cheryshev-Lobato nodes interpolation with the mapping used before. And this is with the new mapping. Of course, the result is very much better because we know where the discontinuity is. And this is a very great information to have. Okay, let's see another example, same technique, more complicated function. The result is replicable with any kind of strange discontinuous function you can imagine. So this is the equispace nodes. These are the fake Cheryshev-Lobato nodes, and these are the fake nodes with the mapping, with a shift in mapping. We can use it also on 3D. So a similar mapping can be used. So you simply put away and shift the nodes where the signal is different, and around the points, around its border, the gradient is higher. So we can simply use that mapping, the shifting, and this is the result in polynomial interpolation approximation, because it's it's least square without and with the fake nodes mapping. A little gift to recap. Was made by Francesco. Thank you for letting me use that. Just to make sure everybody's in. Yeah, it's okay. Suppose that we have the room phenomenon and the Gibbs phenomenon. We apply the mapping. Okay, we forget about the functions. We interpolate the function g. Okay, and then we go back into the original space by applying the same mapping to the evaluating points. Python code is available online for this work if you want to check it out. So, let's talk about the future works. There's a lot of open question about this because it's very simple to apply and very complicated to explain. So what are the optimal, or is there even an optimal mapping either for fixing the couples, nodes, fake nodes? Suppose that you have some nodes and you know exactly where you want to map the nodes. There is plenty of ways to do that, and we don't know yet which is better. What are the conditions on the mapping? To send every space points into Chebyshev-Lobato-like nodes, I mean into nodes that have the same growth of Lebesgue constant of Chebyshev-Lobatos. And what exactly the role of mapping in row propagation. Future works, we want to study it in RBF2. Application to medical images is medical images, which is my field of application. Dispersing approximation, applying splines, and many other possible ideas. The fields of applying are very, very large. So this is all. Thank you everybody for listening to me.